This is our last example on relative motion that appears in your PDF files for lecture notes. In this question, we have a plane with a radar system, and through this radar system, this plane A is observing the flight of plane B. In real-world situation, this is a three-dimensional problem. However, we degrade this problem into a planar problem, and in this planar problem, you could as well fix a frame onto A and call that XY frame, and from that frame you can observe the motion of plane B, and the plane A is also in motion, but it's only doing translation. They are flying at different altitudes. Plane A is at 12 kilometers, plane B is at 18 kilometers. And what happens is aircraft A, this plane A, is increasing its speed at the rate of 1.2 meters per second each second. That means it has an acceleration. Because it's doing direct linear motion, we can directly derive the acceleration information from here. That means it's doing an acceleration of 1.2 meters per second square, increasing its speed. Now, A has a speed of 1000 kilometers per hour at the instant. When theta is 30 degrees, this angle is 30 degrees. And we are asked to determine the change in our dot, which is our double dot in that sense, the second derivative of r, that means, and the second derivative of the theta, the change in theta dot. That means we are going to deal with accelerations here, because this information appears in the acceleration equation for the polar coordinates, right? If I just try to remember what those were, we had r double dot minus r theta dot squared. This is the radial portion of our acceleration, and then we had 2 r dot theta dot plus r theta double dot, and that was the e theta part. So this part is the accelerations a theta, and this part is ar. Now, this information of r double dot and theta double dot are already embedded within these acceleration components of ar and a theta. Okay, now what we know here is that the type of observation done here is a relative motion measurement. Therefore, this acceleration that we are talking about here is acceleration of B with respect to A. Acceleration of plane B with respect to plane A, or acceleration of plane B as observed by plane A. Therefore, we need to write out our equation for acceleration, and in that case, the absolute acceleration of B would be equal to absolute acceleration of A plane plus the relative acceleration of B with respect to A. Okay, this is our equation in the acceleration level. And what we are trying to find out is acceleration of B with respect to A, and after that point on, we're going to do our calculations to find r double dot and theta double dot. Therefore, from this equation, I can find the relative acceleration as the acceleration of absolute acceleration of plane B minus the absolute acceleration of plane A. So far, so good. And then, do I have that information about the acceleration of A and B? What is given to me is that A has an acceleration of 1.2 meters per second squared in this axis, which is x-axis. And then the plane B has a constant speed, so that means its acceleration is equal to 0. So I can directly calculate the relative acceleration as the acceleration of B is equal to 0, okay, a 0 vector, minus the acceleration of A, that would be 1.2 meters per second square. Along which direction? If I call this x-axis, then this will be I, this will be j vectors defining the direction of these axes. Therefore, this will be 1.2 I. Okay, meters per second squared. That is our relative acceleration AB. Now, based on this information, I could get the information of AR and A theta. How do I do that? Well, first off, I need to find out this ER and E theta unit vector directions. How do I do that? Well, this is my R vector, and along the R vector, along this direction, there is the ER unit vector, and theta is defined from this x-axis in 30 degrees in this way. Therefore, in this direction will be with 90 degrees to ER will be E theta. Now, after this point on, based on this 30 degrees, and this is 30 degrees as well, I can now find, this is also 30 degrees, I can now find the E theta and ER unit vectors in terms of I and J. And if I can do that, then the next step will be taking the projection of this relative acceleration onto the ER and E theta directions. And as a result of that, I will find the AR and A theta components. So my aim for finding AR is to take the dot product of this relative acceleration with ER vector, and this is a unit vector, right? So the magnitude is going to be 1. Its magnitude is 1. It's not going to change the magnitude of the acceleration. It's not going to have an effect on it. And then the next thing I can do is to find a theta component. Now I will do the projection again by taking the dot product of this relative acceleration with E theta. That means I can find these A theta and AR components, and I can write out this ER vector quickly, and this will have a component in X, this will have a component in Y. The component along the X direction is cosine 30 degrees. Since it's along the X direction, it's I, and then in the Y direction is a positive Y, and that will be plus sine 30 degrees J. That's my ER vector. E theta vector would be, in the x-axis it's in the negative direction, so there will be negative sine 30 degrees I and a plus cosine 30 degrees J. That's my E theta unit vector. And as I've already found the relative acceleration, all I need to do is take the dot products and find these components. Okay, that's good so far. I find the AR component and a theta component, but what is asked in the question is for me to find this R double dot and theta double dot. That means I have to also find out this R, theta dot, R dot information. R could be found easily because now if this is R length and this is the altitude, and if this is 30 degrees, then I know that this difference, and this is 6,000 meters, and from 30 degrees I will be able to find R as 6,000 divided by sine 30 degrees, right? That's my R value, so it's easy to find. How about theta dot and R dot? Well, that information will be found from the velocity information. Remember that by this is the velocity of B with respect to A. Sorry, A with respect to B. Okay, yes, this is the B with respect to A. Sorry for that. Okay, velocity, relative velocity of B with respect to A. And here R dot is along ER direction, plus we got R theta dot along the E theta direction. Now I need to find the relative velocity between these two planes. the relative velocity vector. Both planes travel along the x direction. Therefore, in a similar way, I can write out the velocity information. Let me just move a little bit down so that I will have more space to write. Okay. So what I need to do is write out an equation for velocity of B. Absolute velocity of B is equal to absolute velocity of A plus relative velocity of B with respect to A. And this is the component I'm looking for. Therefore, velocity of B with respect to A is equal to absolute velocity of the B plane minus the absolute velocity of the A plane. And from here, I will get a numerical value, which is, we can just calculate. If this is 1,500 and the other one is 1,000, then the difference is 500 kilometers. This is 500 kilometers in the A direction, 500 kilometers per hour. Obviously, you need to change this into meters per second, and this is how you would change that. Multiply with 1,000, divide by 60 times 60, right? And this will get you meters per second for this relative velocity. And after you find the relative velocity, well, it's the similar idea. Now you need to extract this component and that component. How do you extract this component? Well, you need to take the projection of this relative velocity with respect to the ER unit vector. So what you need to do is BA vector dot product ER would give you the information about R dot. Similar to that, the BA relative velocity vector dot product E theta is the projection of this velocity vector, relative velocity vector, along the E theta direction, and that would be equal to R theta dot. We calculated R already, so you can find theta dot, and then you can put these information inside in the equation, and then as a result of that you will get the numerical solution, which is already present over here, step by step. So as you do the necessary calculation to calculate the acceleration vectors R component, that will be equal to R double dot minus R theta dot. As we have this R and theta dot already calculated, then we can calculate R double dot directly. And in a similar manner, as R dot and theta dot are calculated from the velocity equation, then theta dot will be calculated from this component of the acceleration in the E theta direction. And these components are found again by a vector operation, which is the dot product, and the meaning of that is projecting one vector on top of another vector. And if you would have any questions about these, again, you can ask me during the lecture hour.